Deep inside one of the Milky Way's most crowded star clusters, Hubble has detected something that should not be there. A seemingly ordinary star is moving in a precise orbit around an object that produces no visible light. It could be a faint stellar remnant, a neutron star, or even a hidden black hole, but the evidence still refuses to give scientists a final answer. Stay with us as we follow the clues into the darkness. And before we begin, like the video and subscribe for more calm journeys through the mysteries of space. Ko the dokcham voi nipbi ande dat koang 30 giai. Far beyond the bright disk of the Milky Way, a community of old stars moves through the galaxy's halo. This region surrounds the thinner spiral disk like a dim, extended sphere. It contains scattered stars, gas-dark matter, and ancient clusters that formed during the early history of the galaxy. Among these clusters, Omega Centauri appears large and complex. From Earth, it lies in the direction of the southern constellation Centaurus, where it can look like a soft patch of light under a dark sky. Its glow comes not from a cloud or a single star, but from millions of stars gathered into one gravitational system. Omega Centauri lies about 17,000 light-years from Earth. The light-reaching telescopes today begins its journey long before recorded history. During that passage, it crosses the sparse space of the galactic halo and then travels through regions influenced by the Milky Way's disk. Small amounts of dust can absorb and scatter part of the light, yet the cluster remains one of the brightest globular clusters visible from Earth. A globular cluster is a nearly spherical collection of stars held together by their shared gravity. Most such clusters contain very old stars and travel around the wider galaxy on long paths that differ from the more orderly motion of stars within the disk. The cluster extends across hundreds of light-years, although most of its visible light is concentrated toward the middle. Its outer boundary does not end sharply. Instead, the number of member stars gradually falls with distance from the center until the cluster blends into the surrounding stellar field. Gravity keeps the main body together while the Milky Way exerts a pull across the entire system. Stars near the outer regions feel both influences. Over long intervals, some may drift away, adding faint streams to the halo. The remaining population continues to orbit the cluster's common center, each star following a path shaped by the combined mass of all the others. Around 10 million stars belong to Omega Centauri. They do not form a flat disk, and they do not circle in one simple direction. Their paths tilt through the cluster at many angles, creating a three-dimensional swarm. From a distance, the separate motions merge into a calm point of light. At closer resolution, the field becomes crowded with stars of different colors and brightnesses. Many appear yellow or orange because they are old and have changed during their long lives. Others remain small and faint, burning hydrogen slowly. A limited number appear blue often because their histories include interactions, mergers, or unusual stages of stellar evolution. The great age of the cluster is written into its population. Most of its stars form many billions of years ago when the Milky Way is still assembling. Their chemical composition preserves traces of the gas available at that time. Astronomers use the word metallicity for the amount of elements heavier than hydrogen and helium inside a star. In many globular clusters, most stars share a similar metallicity because they form during a relatively brief episode. Omega Centauri differs. Its stars show several chemical groups and a noticeable spread in ages and compositions. This diversity suggests that star formation continues in separate periods using gas enriched by earlier generations. Such complexity makes Omega Centauri different from a simple cluster born all at once. One widely studied possibility identifies it as the remaining central region of a small galaxy that the Milky Way absorbs long ago. In this view, the outer stars of the smaller galaxy are stripped away by tides while its dense nucleus survives. Observations support parts of this picture, including the cluster's large mass, its varied chemistry, and its multiple stellar populations. The complete history remains uncertain, and different models describe how the system loses material and settles into its present orbit. The cluster therefore carries both the order of a bound stellar system and the layered record of a more complicated origin. Across the wider field, stars that belong to the Milky Way appear in front of and behind the cluster. Some are nearby disk stars, while others occupy the distant halo. Their apparent closeness on the sky does not mean that they share the same location in space. A bright foreground star may lie thousands of light years nearer than a faint cluster member beside it. Background galaxies also appear between the points of starlight, although many are difficult to separate in crowded regions. Distance, color, brightness, and motion help astronomers decide which sources belong to Omega Centauri and which merely lie along the same line of sight. The cluster's stars remain separated by enormous distances, even where the sky appears full. In its crowded regions, however, the average spacing is far smaller than it is around the Sun. A typical star near the Sun has no neighbor within several light years. Within dense parts of Omega Centauri, stars can be separated by only a fraction of a light year. Direct collisions are still uncommon because stars are tiny compared with the spaces between them. Gravitational encounters are more important. Passing stars gently alter one another's paths, exchanging energy over millions and billions of years. These countless small interactions slowly reshape the distribution of mass within the cluster. The entire system moves through the Milky Way while also turning within itself. Its collective path carries it above and below the galactic plane through a halo dominated by gravity rather than bright gas and young stars. Inside the cluster, faster and slower members cross the field in different directions. Some massive objects tend to settle toward denser regions through repeated gravitational encounters, while lighter stars can gain energy and move outward. This gradual sorting is not perfect, especially in a system as large and complex as Omega Centauri, but it influences the arrangement seen across the cluster. From Earth, the result is a layered field of light. The Milky Way provides the distant setting, the halo provides the broad environment, and Omega Centauri forms the bound stellar island within it. Its outer stars fade gradually into the surrounding sky, while its combined glow marks a structure far larger than any ordinary star system. Every point belongs to a moving universe, and every measured position rests within this broad arrangement of galaxy halo cluster and stellar crowd. Hubble observes Omega Centauri from an orbit above Earth's atmosphere, where the light of distant stars reaches its instruments without passing through the moving air that blurs ground-based images. The telescope circles Earth while remaining within the planet's gravity. From this position, it gains a stable view of the sky. Its cameras record crowded stellar fields with sharp detail separating points of light that would otherwise overlap. This clarity allows astronomers to examine the cluster not as a single glow, but as a dense arrangement of individual stars. The telescope gathers light with a primary mirror about 2 meters across. The mirror directs incoming light toward instruments designed to measure brightness, color, and position. Each detector is divided into many small picture elements. A star does not fall onto only one element because diffraction and the shape of the optical system spread its light into a tiny pattern. Astronomers study the center of that pattern to estimate where the star lies on the detector. The estimate can be more precise than one picture element. Careful calibration turns each small patch of recorded light into a measurement of position. Omega Centauri presents a demanding target because so many stars appear close together. In the densest regions, the light patterns of neighboring stars can overlap. A bright giant may spread light across faint stars nearby, and small changes in focus can alter the recorded shape. Astronomers use optical models to separate these blended sources. They compare the expected pattern of a single star with the pattern recorded in the image, adjusting the model until the positions and brightnesses fit. This process is repeated across the field where thousands of stars may occupy a single exposure. Hubble does not hold perfectly still during an observation. Small motions arise from guidance, thermal changes, and movement through sunlight and shadow. Fine guidance sensors track selected stars and help keep the telescope pointed steadily. Even so, each exposure contains slight shifts that must be measured. Astronomers compare many stable stars and correct the remaining motion. The crowded field becomes useful because it provides a dense reference pattern. A change affecting the whole image can be separated from the motion of one particular source. The detector also introduces small distortions. A straight grid in the sky does not appear as a perfectly straight grid in the raw image because the optics and camera geometry bend positions by tiny amounts. These effects are mapped through calibration. The measured location of each star is corrected according to where it falls on the detector. The telescope's orientation may change between visits, placing the same star on a different part of the camera. This makes calibration essential. Without correction, instrumental distortion could imitate a stellar displacement or hide a real one. A single image shows where a star appears at one moment. Motion becomes visible only when images taken at different times are compared. Hubble returns to the same field after months or years, recording another set of positions. The images are aligned using surrounding stars. Astronomers account for changes in scale rotation and detector placement, creating a shared coordinate system. The position of each source is then compared across the observing dates. Most stars shift because they move through the cluster and are viewed from changing locations. The apparent motion of a star across the sky is called proper motion. It is measured as an angular change rather than as a direct distance. At the distance of Omega Centauri, even a star moving rapidly may shift by only a tiny fraction of a second of arc during a year. A second of arc is 1/3600th of a degree. Hubble can measure changes far smaller than this when observations are combined. The precision comes from repeated exposures, stable optics calibration, and many reference stars. Earth's yearly journey around the Sun also changes the apparent position of nearby objects. This effect is called parallax. A star seems to move against more distant sources as the observing point shifts from one side of Earth's orbit to the other. For a distant cluster such as Omega Centauri, the parallax is extremely small, but it still belongs in the full model of observed motion. Astronomers also consider the movement of the cluster as a whole. The shared drift of many member stars is separated from the individual motion of each star within the cluster. Brightness measurements support the positional work. Hubble records stars through different filters which allow selected ranges of wavelength to reach the detector. Comparing these measurements gives information about stellar temperature and helps distinguish one source from another. A star that appears blended in one filter may be easier to separate in another if nearby stars have different colors. Multiple exposures also reveal detector effects, cosmic ray strikes, and temporary imperfections. A cosmic ray can create a bright mark in one image, but it does not repeat in the same place across several exposures, so it can be removed during processing. Time becomes a central part of the observation. The longer the interval between images, the farther a moving star travels across the detector. A short interval may show almost no change, while a span of many years can reveal a measurable path. Hubble's long operating history makes such comparisons possible. Images taken for one scientific purpose can later become the first point in a much longer record. New observations add another position, extending the baseline and reducing uncertainty. The telescope, therefore, acts not only as a camera but as a stable measuring instrument spread across time. The final result is a map of changing positions. Each star carries a sequence of measured locations each, with a small range of uncertainty. Astronomers compare these points with models of simple motion. A star traveling freely across the cluster should follow an almost straight path over a limited interval once parallax, and the motion of the cluster are removed. Measurement errors scatter the points slightly around that path. Repeated observations show whether the scatter remains random or whether a consistent pattern appears. Hubble's distant view turns faint points of light into a record of motion built slowly from precision repetition and careful control of every instrumental effect. Within the crowded light of Omega Centauri, one star becomes the central, visible object of the investigation. It does not initially appear unusual. In a Hubble image, it is a small point among thousands of other points, each formed by light that has crossed the cluster and traveled through interstellar space. Its apparent size does not reveal its true diameter, because even a large star remains too distant to be resolved as a disk. What Hubble records instead is its brightness, color, position, and the shape of the light pattern produced by the telescope. The first task is to determine whether the source is truly one star. Crowded fields can make two or more stars overlap so closely that they appear as a single point. Astronomers compare the recorded light pattern with the expected pattern of an isolated star. If the source is broader, uneven, or changes shape between filters, blending may be present. Images taken at different orientations also help, because nearby sources fall across the detector in different ways. When the light pattern remains consistent, the evidence supports the interpretation that one dominant star produces most of the measured light. Brightness gives the first broad clue to the star's nature. The detector counts incoming photons, which are individual packets of light. A brighter source produces more recorded photons during the same exposure. The measured brightness must be corrected for the instrument, the chosen filter, and the amount of dust between the cluster and Earth. Dust absorbs more blue light than red light, making stars appear both dimmer and redder. Astronomers estimate this effect across Omega Centauri so that the star's observed light can be compared with the light expected from known kinds of stars. Color provides a simple measure of temperature. A hotter, stellar surface emits a larger fraction of its visible light at shorter wavelengths, while a cooler surface emits relatively more at longer wavelengths. Hubble records the star through several filters and compares the resulting brightnesses. The differences form a color index, a numerical description of how blue or red the source appears. This does not function as a photograph alone. It is a physical measurement linked to temperature, surface chemistry, dust absorption, and the star's stage of evolution. The star's color and brightness can be placed on a color magnitude diagram. This diagram arranges stars by luminosity and color, allowing large populations to form recognizable sequences. Main sequence stars are still converting hydrogen into helium in their cores. Giant stars have exhausted much of their central hydrogen and expanded into larger, cooler bodies. White dwarfs are compact remnants that remain hot but faint because their surfaces are small. By locating the visible star among the cluster's established sequences, astronomers judge which broad category best fits its light. Membership in Omega Centauri must also be tested. A foreground star can appear in the same direction while lying much closer to Earth. A background star can sit far beyond the cluster. Proper motion helps distinguish these possibilities because cluster members share a general movement across the sky. Distance estimates, color brightness, and chemical composition provide additional evidence. When the star follows the cluster's collective motion and matches one of its stellar populations, it is more likely to belong to the cluster rather than merely align with it by chance. The distance to the cluster then allows apparent brightness to be translated into luminosity. Apparent brightness describes how much light reaches the telescope. Luminosity describes how much energy the star releases in all directions. A weak nearby star can appear brighter than a powerful distant star, so distance is essential. Once the common distance of Omega Centauri is adopted, astronomers compare the measured light with stellar models. These models connect luminosity and temperature to mass, radius, age, and chemical composition, although every estimate retains some uncertainty. The visible star is likely an ordinary low-mass member of an old population. Such stars can survive for many billions of years because they consume hydrogen slowly. Their interiors remain balanced between inward gravity and outward pressure generated by hot gas and nuclear reactions. In the core, hydrogen nuclei combine through a sequence of reactions that eventually forms helium. Energy moves outward through radiation and convection before leaving the surface as light. The process is steady on human time scales, and the star's overall appearance changes only gradually. A spectrum can reveal more detail when enough light is available. A spectrum spreads the star's light into its component wavelengths. Dark absorption lines appear where atoms in the outer layers remove light at particular wavelengths. Their patterns identify elements such as hydrogen, calcium, iron, and magnesium. The strengths and shapes of these lines provide estimates of temperature, surface gravity, and chemical abundance. In a cluster with several stellar populations, chemistry helps connect the star to one formation group and separates it from stars that formed from gas with a different history. Spectral lines also show motion along the line of sight through the Doppler effect. When the star moves toward Earth, its lines shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. This radial velocity complements Hubble's measurement across the sky. Repeated spectra can establish whether the visible atmosphere remains stable and whether changes arise from ordinary stellar activity. Cool stars may display spots, convection, or magnetic effects, but these usually alter brightness and line shapes within limits understood from other stars. The star's light, therefore, provides a quiet physical portrait. It has a measurable temperature, luminosity, color chemical pattern and place within the cluster's population. Its surface is visible only through the radiation escaping from a distant point. Yet that radiation carries information from layers near the top of the stellar atmosphere. No unusual glow-extended structure or obvious second source is required to explain its appearance. In ordinary images, it remains a normal member of an ancient system sustained by the same balance of gravity, pressure, and nuclear energy that governs countless other stars in Omega Centauri. Its measured properties also remain subject to uncertainties. Photometric calibration, dust correction, crowding, and model assumptions each contribute to the range. Astronomers carry these uncertainties through every estimate rather than treating one value as exact. The resulting description is precise enough to classify the star while preserving the limits of the light. Across the crowded field of Omega Centauri, the visible star changes position by an amount too small to notice in one image. Hubble records that change through observations separated by months and years. Each exposure fixes the star against neighboring sources. When the images are aligned, the star does not remain in the same place. Part of the shift belongs to the motion of the entire cluster. Part belongs to the star's own travel within the cluster, and part comes from the changing viewpoint of Earth as it moves around the Sun. Astronomers begin by building a reference frame from many cluster members. A reference frame describes position and motion relative to selected objects. Stars that share the movement of Omega Centauri provide a stable local pattern, even though each one also has a small individual velocity. By averaging over many stars, common motion becomes measurable and random stellar motions cancel. The visible star can then be compared with this shared frame rather than with the detector alone. The first model is simple. Over this period, a star moving freely through space should trace an almost straight line across the sky. Its speed and direction remain nearly constant because the interval is short compared with the cluster crossing time. Cluster gravity bends the path gradually. Parallax adds a small yearly pattern, and the motion of the telescope introduces known observational changes. Once these effects are included, the expected position at every observing date can be calculated. Each Hubble exposure provides a measured point with uncertainty. The uncertainty is not a sign that the position is unknown. It describes the small range within which the true position is likely to lie. Brightness crowding, detector noise focus, and the placement of the star on the camera all affect this range. A bright, isolated star can be measured more precisely than a faint, crowded star. Repeated exposures reduce random error because accidental shifts do not usually occur in the same direction every time. The images enter a common coordinate system. This requires correcting rotation, scale distortion, and translation. Nearby reference stars define how one image maps onto another. Astronomers reject sources affected by saturation detector defects or severe blending. They also examine whether the star falls close to a bad picture element or a cosmic ray mark. A reliable measurement survives these tests across many images and many observing dates. When the visible star's positions are plotted against time, most of the movement follows the expected drift. It travels through the cluster with a proper motion, consistent with membership. The path is not dominated by a sudden jump or an isolated bad measurement. Instead, small differences appear repeatedly. At one time, the star lies slightly to one side of the best straight path. Later, it lies slightly to the opposite side. The shift is tiny, but the direction of the departure changes in a coordinated way. A random measurement error would scatter points randomly. Some would fall above the model, some below, and the pattern would not repeat. A systematic instrumental effect could produce an ordered shift, but it would often influence other stars in that image or depend on detector position. Astronomers therefore compare the visible star with nearby sources with similar brightness and color. If only one star shows the changing displacement while others remain consistent with straight motion, an explanation tied to that star becomes more likely. The star's brightness is monitored at the same time. A changing center of light can occur when two unresolved stars vary in brightness. As one source brightens, the combined point appears to move toward it even if neither star moves. This effect is called variability-induced motion. The Hubble measurements are checked for correlated changes between brightness and position. Strong blending can also shift the measured center when telescope orientation changes. Stable brightness and a consistent light pattern weaken these alternatives, although they cannot remove every uncertainty. The yearly motion of Earth requires careful treatment. Parallax produces a small apparent ellipse whose size depends on distance and direction on sky position. Because the cluster is distant, the effect is very small, yet the precision of Hubble makes it relevant. Observation dates at different points in Earth's orbit help separate parallax from a slower positional drift. The cluster's common distance provides an additional constraint, but the analysis still allows for a range rather than assuming one exact value. Perspective can also change apparent proper motion. A system moving toward or away from Earth may seem to expand or contract across the sky. This perspective effect is tiny for one star over this baseline, but precision studies account for it. Internal motions within the cluster add another layer. Nearby stars may have different velocities because their orbits through the cluster are different. Their distribution shows whether the visible star's overall speed is ordinary for its location. The unusual part of the path is not its total speed. The star does not race away from the cluster or move like a foreground object. Its broad motion remains compatible with the surrounding population. The difference is the small departures from constant motion. These departures persist after the main proper motion parallax image, distortion, and shared cluster drift are fitted. Their scale appears in extremely small angles, yet the long observing baseline turns them into a coherent record. Astronomers test many motion models. They remove individual exposures, alter the reference. Stars change, calibration choices, and fit separate filters. A genuine signal should remain within expected uncertainty. If the displacement vanishes whenever one image is excluded, the evidence is weak. If it survives independent reductions and appears across several observing periods, confidence increases. It also persists across independent filters and telescope orientations without a comparable pattern among nearby reference stars defining the field. The result is not a final explanation. It is first recorded as astrometric acceleration, meaning the star's apparent sky velocity changes with time. This acceleration defines the anomaly without naming its cause. The visible star follows the cluster while making a small ordered deviation from a straight path. The measurement uses many points, each corrected for known effects and compared with a local stellar frame. What remains is a motion that constant travel does not fully describe, preserved in the slow displacement of one point of light. The changing motion of the visible star becomes clearer when its measured positions are considered as parts of one continuous path. A straight line no longer fits the record adequately. The star appears to speed up in one direction, slow in another, and bend gradually across the local reference frame. They connect smoothly through time, suggesting that the star is following a curved route rather than experiencing unrelated shifts. A curved stellar path can arise when gravity pulls the star toward another concentration of mass. In a bound system, neither body remains fixed. Both move around a shared center of mass, a point determined by how their masses are distributed. The more massive body stays closer to this point, while the less massive body traces the wider path. If one body emits the detectable light, Hubble records only the motion of that visible component. It is the path of the luminous star around their common balance point. Astronomers describe such motion with an orbital model. The model includes the time required for one cycle, the shape of the path, its orientation in space, and the position of the system along that path at each observing date. A circular orbit is the simplest case, but most natural orbits are ellipses. An ellipse is a closed curve with two focal points. The shared center of mass lies at one focus rather than at the geometric center. The star moves faster near the closest part of its orbit and more slowly near the farthest part. The orbit does not appear in its true shape on the sky. It is projected onto a flat image from a distant viewpoint. A circular path seen face-on appears circular, while the same path seen at an angle appears compressed into an ellipse. A truly elliptical orbit may look more or less stretched, depending on its tilt. Astronomers must therefore separate the actual orbital shape from the effect of projection. They fit many possible orientations and compare the predicted positions with the measurements. Several angles define this orientation. One angle describes the tilt of the orbital plane relative to the plane of the sky. Another marks the direction where the orbit crosses that plane. A third sets the orientation of the ellipse within its own plane. These quantities are not visible directly in one image. They emerge from the sequence of positions. When the star curves northward, then eastward, then back through the reference frame, the order and size of those changes constrain how the orbit is turned in three-dimensional space. The observing record may cover only part of a complete cycle. In that case, many different orbits can reproduce a short arc. A broad orbit viewed at one angle may resemble a smaller orbit viewed at another. A highly elongated path may imitate part of a nearly circular one if the measurements fall near a quiet section. The uncertainty remains large until the star has moved through enough of the curve to reveal changes in direction and speed. Each new observing date narrows the range of models by extending the measured arc. A repeating pattern provides stronger evidence than acceleration alone. Acceleration shows that the velocity changes, but repetition indicates a bound cycle. When the star returns toward an earlier direction of motion after a consistent interval, the positions begin to outline a closed path. The measured points need not reach exactly the same detector location because the entire system continues moving through Omega Centauri. Astronomers first remove the broad proper motion. The remaining positions can then be examined as motion around a local center. This separation produces two layers of movement. The first is the steady travel of the system through the cluster. The second is the smaller orbital motion carried along with it. The combined path resembles a gently wavering line across the sky, while the corrected orbital path forms a compact curve. The center of this curve is not a material object visible in the image. It is a mathematical point that remains nearly fixed once the system's overall movement has been removed. The timing of the positions also matters. Points recorded at equal intervals do not always lie at equal distances along the apparent orbit. This uneven spacing reflects changing orbital speed and projection. If the path is elliptical, the star covers more of its orbit when it passes closer to the shared center of mass and less when it is farther away. The observed spacing can therefore distinguish a physical orbit from a simple geometric curve fitted without regard to gravity. Keplerian motion provides the basic description. A Keplerian orbit is the path followed by two bodies whose motion is dominated by their mutual gravity. The model treats the bodies as concentrated masses and assumes that outside forces change the orbit only slightly during the observing span. In the crowded environment of Omega Centauri, distant stars exert additional pulls, but these are usually weak over one compact orbital cycle. The local two-body model remains a useful first approximation. Astronomers compare the calculated orbit with every measured position. They allow the parameters to vary within broad ranges and identify combinations that produce the smallest residuals. A residual is the difference between a measured point and the position predicted by the model. Good models leave small residuals without an ordered pattern. Poor models leave systematic departures, such as all early points lying on one side and later points on the other. The quality of the fit depends on honest treatment of uncertainty. Measurements with smaller errors carry more weight, while less precise points influence the result less strongly. Alternative calibrations are tested to ensure that the orbital curve does not depend on one reduction choice. Nearby stars are analyzed in the same way, providing a check against false curves created by the reference frame. The resulting path remains invisible in ordinary images across the surrounding stellar field because no line connects the separate observations. It exists only after time is added to the field. One point of light occupies a sequence of slightly different locations, and those locations form a gravitational pattern. The visible star is not wandering randomly, it is moving around a center that gives no light of its own, while the entire system continues its quieter passage through the ancient cluster. The hidden companion cannot be seen directly, but its gravity appears in every measured part of the visible star's orbit. Gravity changes motion in a predictable way. A stronger pull produces a tighter curve, a greater acceleration, or a shorter orbital period for a given separation. By measuring the path carefully, astronomers can estimate how much mass must be present near the unseen center. It depends on the relationship between distance, speed time, and gravitational attraction. The orbital period provides one of the important measurements. It describes the time required for the visible star to complete one full circuit around the shared center of mass. When the observing record covers a complete cycle, the period can be read from the repeating pattern of position and velocity. When only part of the orbit is observed, the period must be fitted along with the other orbital properties. Longer monitoring reduces uncertainty because it shows more of the curve and limits the range of cycles that can match the data. The apparent size of the orbit is measured as an angle on the sky. This angular size must be converted into a physical distance. The conversion depends on the distance from Earth to Omega Centauri. A small uncertainty in the cluster's distance changes the estimated size of the orbit and therefore changes the infrared mass. Astronomers carry this uncertainty through the analysis. They do not treat the cluster distance as perfectly known, even when many independent methods provide a narrow range. Once the physical scale and period are known, the total mass of the system can be estimated through the laws of orbital motion. A wider orbit completed in a short time requires more mass than the same orbit completed slowly. The result gives the combined mass of the visible star and the unseen companion. The mass of the visible star is then estimated from its brightness, temperature, chemical composition, and evolutionary state. Subtracting that contribution leaves a range for the hidden object. This process is more complex when only the visible star is measured. The observed orbit is not necessarily the full separation between the two bodies. It is the visible star's path around the shared center of mass. If the companion is much more massive, the visible star traces most of the system's relative orbit while the companion moves through a smaller path. If their masses are similar, both travel through comparable distances. The relation between these paths depends on the mass ratio, which must be included in the model. The center of mass divides the distance between the two bodies according to their masses. The heavier body lies closer to that center, while the lighter body lies farther away. If the visible star has a known approximate mass, the size of its orbit helps constrain the companion's mass. A large visible orbit around a nearly fixed center suggests a heavier, unseen object. A smaller visible orbit can be produced by a less massive companion, although orbital orientation can alter the apparent size. Projection remains important. An orbit tilted toward the line of sight appears narrower on the sky than the same orbit viewed face-on. Astrometry measures movement across the sky, while spectroscopy can measure motion toward and away from Earth. Combining these two directions reveals the three-dimensional velocity. When radial velocity measurements are available, they help determine the orbital tilt and reduce ambiguity. The visible star should alternately approach and recede as it travels around the shared center, producing a repeating shift in its spectral lines. The amplitude of this radial motion depends on the star's speed and orbital orientation. A face-on orbit produces little change along the line of sight, even if the star moves rapidly across the sky. An edge-on orbit produces a stronger radial signal. Weak or incomplete spectra do not necessarily contradict the astrometric orbit. They may reflect a low inclination effect, faintness crowding, or limited measurement precision. The strongest analysis combines all available observations while preserving the uncertainty of each. The shape of the orbit also carries information. In an elongated orbit, the visible star accelerates as it approaches the point of closest separation and slows as it moves outward. The rate of this change depends on the total mass and the geometry of the path. Measurements near the closest passage are especially valuable because the gravitational effect is strongest there. However, those observations may be difficult to obtain if the event occurs between scheduled telescope visits. Astronomers often explore many possible parameter combinations rather than selecting one solution immediately. Computer models draw trial values for period eccentricity, orientation, distance, system motion, and mass. Each trial predicts where the star should appear at every observing date. Models that fit within the measurement errors are retained. The collection of accepted models forms a probability distribution showing which masses are more likely and which remain possible but less supported. It may include several classes of companion, each occupying part of the allowed range. The central estimate provides a useful summary, but the full interval is scientifically more important. A mass near one value does not establish a unique identity. When measurement uncertainty, stellar mass estimates and projection remain connected. Continued observations can shift the preferred range or divide one broad solution into narrower alternatives. External gravity from the cluster is also considered. Omega Centauri contains millions of stars, whose combined mass shapes the motion of every member. Across a compact, binary orbit, this background field is usually nearly uniform, so both bodies experience almost the same acceleration through the cluster. Their relative motion is therefore dominated by their mutual gravity. A close passing star could disturb the orbit, but such encounters are uncommon during a short observing span. The ordered and repeating motion is more consistent with a bound pair than with a temporary distant pull. The final mass estimate emerges from the orbit as a measured gravitational requirement. The visible star's path demands a certain amount of unseen mass near the local center. That mass is not inferred from darkness alone. It is inferred from the speed, curvature, timing, scale, and orientation of the motion. Light describes the visible star, while gravity describes the whole system. The difference between those two descriptions defines the hidden companion as a physical presence, even before its nature is known. The orbital solution points toward a second concentration of mass, yet the images show no obvious second star beside the visible one. This absence becomes a measurement of its own. Astronomers do not simply look at the field and declare the companion dark. They calculate how much light another object could produce without being detected. Then compare that limit with the brightness expected from ordinary stars of different masses, ages, and temperatures. Hubble's sharp vision is important because the system lies in a crowded part of Omega Centauri. Nearby stars can overlap with the target, and their combined light can hide faint sources. Astronomers examine images taken through several filters at several orientations and during different visits. A real companion that is separated enough from the visible star may appear as a small additional peak in the light pattern. If the pair is too close to resolve, its light may still change the shape, color, or total brightness of the source. The first test searches for a resolved point of light. The expected position of the companion changes as the orbit advances, but its location remains connected to the measured center of mass. Astronomers inspect the region where the orbital model places it at each observing date. They compare the image with nearby isolated stars and with synthetic patterns created from the telescope's optics. No stable second point appears at the predicted locations. Random specks detect a noise, and unrelated background stars do not follow the orbit from one observation to another. The second test studies the combined light. Two unresolved stars usually produce more total light than one star alone. If the companion has a similar temperature, the system may appear unusually bright for the visible star's place on the color magnitude diagram. If the companion is hotter or cooler, it may alter the measured color. Astronomers compare the source with other cluster stars that share the same chemical population and evolutionary stage. The target's brightness and color remain consistent with a single ordinary star within the limits of calibration and crowding. A normal star's mass and luminosity are closely connected during most of its lifetime. A star more massive than the Sun usually burns fuel faster and shines more strongly. A low-mass star is fainter, redder, and longer-lived. In an old cluster, the most massive ordinary stars have already left the main sequence. Even so, a companion with enough mass to explain a strong gravitational pull should generally contribute detectable light unless it has evolved into a remnant or is hidden by unusual circumstances. Astronomers calculate detection limits by adding artificial stars to the images. These artificial sources have known brightnesses and positions. The processing software then attempts to recover them in the same crowded conditions as the real data. A bright inserted star is found easily. As the artificial source becomes fainter, recovery becomes less reliable. The faintest brightness detected with acceptable confidence defines a practical limit for that part of the image. This method includes the effects of nearby stars' detector noise and the complex background. The limit changes with wavelength. A cool red companion may be weak in a blue filter, but more visible in a red or near-infrared filter. A hot remnant may appear more clearly at shorter wavelengths. Observations across several filters therefore test different physical possibilities. Dust affects each wavelength differently, but both stars in the system lie behind nearly the same dust column, so their relative colors remain informative. No filter reveals an additional source that consistently shares the expected orbital location. The spectrum can also contain hidden light. If two luminous stars orbit each other, each may produce its own set of absorption lines. Their lines shift in opposite directions as the stars move around the center of mass. This creates a double-lined spectroscopic binary when both contributions are strong enough. In other cases, the companion's lines may be weak, but still distort the visible star's spectrum. Available spectra are examined for repeated secondary features, unusual broadening, or changes linked to orbital phase. Crowding complicates this work because light from unrelated nearby stars can enter the spectrograph. Their lines may imitate a companion at one observation but remain fixed relative to the cluster rather than following the orbit. Repeated measurements and precise knowledge of the instrument's aperture help separate contamination from a bound source. The visible star's spectrum remains dominated by one stellar atmosphere. Any secondary luminous contribution must lie below the sensitivity of the observations. A companion could be concealed behind the visible star at one moment, but an orbit changes the projected separation with time. It could also be dimmed by surrounding dust, although a compact cloud within an old globular cluster would require evidence from color changes, infrared emission, or variable absorption. No such evidence appears clearly. The darkness is therefore treated as an observational limit rather than as proof of perfect invisibility. The cluster's distance makes even a sun-like star faint, but Hubble detects large numbers of stars below the sun's luminosity in the same field. This provides a direct comparison. If the companion belonged to an ordinary stellar class brighter than the local detection limit, a source of similar brightness should appear. The absence of that source removes part of the possible mass range for a normal star. Uncertainty remains near the threshold. A very faint star can be lost in the wings of the visible source hidden by a neighbor or confused with detector structure. The infrared orbital separation may also be smaller than the resolving power at some phases. Astronomers therefore state limits with confidence ranges and test how those limits change under different assumptions. The result is not that no light exists at all. It is that any companion light is weaker than expected for many ordinary objects capable of producing the measured gravitational influence. The images thus create two linked descriptions. Motion requires additional mass, while photometry allows little additional light. The more tightly these limits overlap, the less room remains for a normal, luminous companion. The hidden object is defined not by an empty patch in one photograph, but by repeated failure to detect the light that a conventional star should contribute. This mismatch is quiet, measurable, and persistent across observations made with different filters, orientations, exposure times, and reduction methods. The absence of an obvious second source does not immediately require an exotic object. Astronomers first examine whether ordinary matter could remain hidden within the limits of the images and spectra. Each possibility must satisfy two conditions. It must provide enough mass to produce the measured orbit, and it must remain faint enough to escape detection. The comparison is made because a crowded cluster can conceal light blend nearby sources and complicate estimates of stellar mass. The simplest possibility is a low-mass main sequence star. Such a star burns hydrogen slowly and can survive for longer than the age of the universe. It is cooler, smaller, and much fainter than the Sun. In the distance of Omega Centauri, a very low-mass star can be especially difficult to detect beside a brighter companion. Its red light may also blend into the visible star's outer light pattern. Astronomers therefore compare the required companion mass with the luminosity expected from old low-mass stars in the cluster. This test has a clear limit. The lower the mass of a main sequence star, the weaker its gravitational influence becomes for a given orbit. A companion faint enough to remain hidden may not provide enough mass to explain the observed acceleration. A companion massive enough to satisfy the orbital model should usually emit more light than the detection limits allow. The exact boundary depends on the visible star's estimated mass, the orbital tilt, the cluster distance, and the completeness of the images. Within uncertainty, some low-mass solutions may remain possible, but much of the ordinary stellar range becomes difficult to support. A brown dwarf offers another faint possibility. A brown dwarf forms in a manner similar to a star, but never gains enough mass to sustain ordinary hydrogen fusion in its core. It cools and fades with age, making an ancient brown dwarf extremely dim at visible wavelengths. In an old cluster, such an object could escape direct detection. Its weakness lies in its mass. Brown dwarfs are less massive than the lightest true stars. If the orbit requires a companion substantially heavier than this range, a single brown dwarf cannot account for the gravitational pull. Astronomers also consider whether several faint bodies could act together. A compact group of low-mass stars, brown dwarfs, or massive planets might provide more total mass than one object, while dividing the light among several faint sources. The group would need to occupy a region smaller than the measured orbit and remain gravitationally stable. In a dense stellar environment, a loose collection would be disturbed by internal interactions and passing stars. A tightly packed group would experience close encounters, energy exchanges, and possible collisions or ejections. The combined brightness of such a group also matters. Several low-mass stars may each be faint, but their total light can exceed the observational limit. Their different positions could broaden the source or produce irregular changes as the visible star moves. A compact cluster of dark substellar objects would avoid some of the light, yet its long-term survival would be uncertain. Dynamical models test how quickly such a group would expand, merge, or lose members. An explanation that survives for only a brief fraction of the cluster's age is possible in principle, but statistically less likely. An unrelated background star can imitate a faint companion in one image, especially in a crowded field. It cannot easily imitate the orbital gravity. A distant source aligned near the target may add light or distort the measured center, but it does not remain connected to the visible star's repeating motion unless the alignment changes in a very particular way. Images taken across years reveal whether a suspicious point shares the same proper motion. A background object should drift relative to the cluster as the cluster moves across the sky. A foreground star creates a similar problem. It may appear close in projection while lying much nearer to Earth. Its color and proper motion can differ from the cluster population. If unresolved, it may shift the apparent position of the target as telescope orientation changes. Astronomers test this by examining nearby reference stars, comparing filters, and modeling two blended light sources. A chance alignment can explain some astrometric irregularities, but it must reproduce the full timing direction and repeated curvature of the observed path. Stellar variability provides another ordinary explanation. A spotted or pulsating star can change brightness across its surface. If the image is blended with a neighbor, the center of light may move as one component brightens or fades. This can create an apparent wobble without real orbital motion. The test compares brightness changes with position changes. A variability-induced shift should correlate with the light curve. When the source remains photometrically stable while the astrometric displacement continues, this explanation becomes less effective. Surface activity can also alter spectral lines and produce apparent radial velocity changes. Large star spots suppress light from parts of a rotating surface, shifting the average profile of absorption lines. Convection and magnetic activity can add further noise. These effects are common in some young or active stars, but Omega Centauri is dominated by old stars. The target's color brightness and spectrum can indicate whether strong activity is plausible. Activity may add small irregularities, yet it does not easily generate a stable astrometric orbit over repeated cycles. Instrumental explanations remain part of the ordinary tests. Detector distortion, charge transfer, focus changes, and imperfect subtraction of neighboring stars can all shift a measured position. A false orbit might appear if observations at similar orbital phases also share similar telescope orientations or detector placements. Independent reductions, therefore, vary the reference. Stars calibration maps, filters, and exposure selections. The signal is compared with nearby stars of similar brightness. An instrumental pattern should usually affect more than one source or depend clearly on detector geometry. No single ordinary explanation is rejected by appearance alone. Each is translated into measurable predictions involving light, color, motion, stability, and timing. Some possibilities fail because they are too faint to provide the required mass. Others fail because they are massive enough but should be visible. Blends variability and detector effects can imitate parts of the signal but struggle to reproduce the complete ordered path. What remains is a narrowing set of conventional solutions constrained simultaneously by the companion's gravitational influence and its missing light. The next step compares the mass required by the orbit with the light allowed by the observations. The orbit describes gravity, while the images and spectra describe radiation. Together they define a range in which the hidden companion must lie. A solution outside that range either fails to move the visible star correctly or produces more light than Hubble should detect. The orbital model does not produce one exact mass. It produces a distribution of possible masses shaped by uncertainties in distance, inclination, period eccentricity, and the estimated mass of the visible star. Some combinations are strongly supported because they fit the measured positions. Others remain possible but require less likely orientations. Astronomers, therefore, use a preferred range rather than a single unquestionable number. The visible star's mass is estimated from its luminosity, temperature, chemical composition, and age. Old stars in Omega Centauri follow evolutionary tracks connecting these observable properties with internal structure. The estimate depends on models of how stars burn fuel and change over time. Small differences in chemical abundance or evolutionary stage alter the result, so the stellar mass enters the orbital analysis with uncertainty. Once the visible star's contribution is included, the remaining mass belongs to the companion. A low value may permit a faint red star or brown dwarf. A higher value may exceed the range in which such objects can exist. The boundary between a brown dwarf and a true star is set by the ability to sustain hydrogen fusion. Objects below that boundary can be very dark when old, but they supply only a limited amount of mass. Objects above it become stars and produce light through nuclear reactions. For ordinary main sequence stars, mass and luminosity do not increase at the same rate. A modest rise in mass can produce a much larger rise in brightness. This relationship matters when the orbital solution suggests a companion comparable to or heavier than the visible star. Such a companion should not remain a minor addition to the total light. It would alter the source's brightness, color, spectral lines, or position within the cluster's color magnitude diagram. An old cluster introduces another limit. Stars born with substantially more mass than the Sun evolve quickly and no longer remain on the main sequence after many billions of years. They expand into giants, lose outer material, and leave compact remnants. A currently massive luminous star in Omega Centauri would therefore require an unusual history such as a merger or mass transfer. These processes occur, but they often leave observable signs, including altered chemistry, rapid rotation, unusual color, or additional light. The hidden mass can also be compared with the cluster's known stellar populations. Hubble observes many ordinary stars at similar distances. Their brightnesses provide an empirical guide less dependent on theory alone. If a proposed companion has the mass of stars visible elsewhere in the same images, its absence beside the target becomes difficult to explain. The comparison is strongest when the expected companion would be brighter than the detection threshold. At lower masses, the distinction becomes less secure. Very faint stars near the hydrogen-burning boundary can hide within the light pattern of a brighter neighbor. Their colors may be difficult to isolate, and crowding can reduce sensitivity. If part of the orbital probability distribution overlaps this region, an ordinary companion cannot be completely excluded. The scientific statement then preserves both facts. The data favor a dark object, while a narrow set of faint stellar solutions may remain allowed. The orbital inclination can widen or narrow this overlap. Astrometry reveals movement across the sky, but an orbit directed partly along the line of sight may contain more motion than the image records. A different inclination changes the physical scale and speed assigned to the orbit. Radial velocity measurements help restrict this angle, yet faint spectra and crowded fields may leave gaps. Models at unusual inclinations can support a different companion mass, though they may fit the full evidence less well. Eccentricity also affects the inferred range. In a strongly elongated orbit, the star's acceleration varies greatly between closest and farthest separation. If observations cover mainly one part of the cycle, the period and total mass can remain connected in several ways. Measurements near the fastest part of the orbit have strong influence. Missing that interval can broaden the accepted solutions. The mass estimate therefore improves as the path becomes more completely sampled. Astronomers also test whether the hidden mass could be divided among multiple bodies. The gravitational field at the visible star may resemble that of one object if several companions remain packed tightly together. Their total mass could fit the orbit while each member produces less light than one larger star. However, ordinary stars still contribute combined luminosity, and a compact multiple system introduces additional motions. The visible star's path may show small deviations from a simple two-body ellipse if the internal companions rearrange their gravitational pull. A group of non-luminous objects avoids the light constraint but faces a stability constraint. Several remnants or substellar bodies confined to a small volume exchange energy through close encounters. Over time, some move inward, some are ejected, and some may collide or merge. The denser the group, the faster this evolution proceeds. Omega Centauri is old, so a temporary compact arrangement requires recent formation or an unusually stable structure. Dynamical calculations can estimate whether such a configuration could survive for much of the cluster's history. The comparison between mass and darkness, therefore, becomes a process of exclusion rather than direct identification. The observations define how heavy the companion appears to be and how faint it must remain. Ordinary stars occupy a region where increasing mass normally brings increasing light. Brown dwarfs remain dark, but at maybe too light. Multiple systems can distribute mass, but add complexity, light, and instability. The surviving range begins to favor matter that carries stellar mass without ordinary stellar brightness. This conclusion remains conditional. It depends on the precision of the orbit, the cluster distance, the estimate of the visible star's mass, and the true detection threshold. None is exact, yet their uncertainties can be combined and tested. The hidden object is constrained not by one dramatic observation, but by the overlap of many quiet limits, each reducing the space in which a luminous companion can remain. The mass-to-light comparison moves the investigation away from ordinary stars and towards stellar remnants. A stellar remnant is the compact object left after a star exhausts the fuel that supports its core. The remnant no longer shines through steady hydrogen fusion, yet it can retain a large fraction of the original star's mass. Its light may become faint enough to escape detection while its gravity remains strong enough to shape the orbit of a nearby star. The kind of remnant that forms depends mainly on the original star's mass. Stars spend most of their lives balancing gravity with pressure generated by nuclear reactions. Hydrogen fuses into helium in the core, releasing energy that moves outward. When the central hydrogen is depleted, the balance changes. The core contracts, the outer layers expand, and new reactions may begin in hotter regions. This later evolution proceeds differently for low-mass and high-mass stars.
A star with a modest initial mass eventually becomes a red giant. Its outer atmosphere expands and
cools, while helium fusion and later shell burning continue inside. Over time, the star loses much of its envelope through winds. The exposed core remains behind as a white dwarf, A white dwarf contains roughly stellar mass, compressed into a body similar in size to Earth. It is supported not by ordinary gas pressure, but by electron degeneracy. Pressure, a quantum effect that resists further compression. A newly formed white dwarf is hot and can shine strongly at first. It has no sustained fusion in its center, so it slowly cools as stored heat escapes. After many billions of years, an old white dwarf becomes faint, especially at visible wavelengths. In an ancient system such as Omega Centauri, a sufficiently cool white dwarf could remain difficult to detect beside a brighter star. Its mass, temperature, and cooling history determine whether it fits both the orbital and photometric limits. White dwarfs have an upper mass boundary. As mass increases, stronger gravity compresses the object further. Electron degeneracy pressure can support only up to a limit near 1.5 times the mass of the Sun, with the exact value depending on composition and rotation. Beyond this range, a stable ordinary white dwarf cannot remain intact. This limit provides a direct test when the orbit suggests a heavier, hidden companion. More massive stars follow a different path. Their cores become hot enough to fuse heavier elements in stages producing carbon, oxygen, neon, silicon, and eventually iron. Fusion beyond iron does not release energy in the same useful way. When an iron-rich core grows beyond the support available from pressure, it collapses rapidly. The outer layers can be expelled in a supernova while the center contracts into a much denser remnant. If the collapsed core remains within a certain mass range, it becomes a neutron star. A neutron star contains more mass than the Sun within a sphere only tens of kilometers across. Matter is compressed beyond ordinary atomic structure. Electrons and protons combine into neutrons in much of the interior, while dense nuclear matter provides resistance against further collapse. The exact structure of the deepest layers remains uncertain because laboratory experiments cannot fully reproduce such extreme conditions. Young neutron stars can be powerful sources of radiation. Some rotate rapidly and send beams of radio waves, visible light X-rays, or gamma rays into space. When a beam crosses Earth, the object appears as a pulsar. Others emit strong X-rays from hot surfaces or magnetic activity. These energetic signatures fade as the neutron star cools and slows. An old neutron star without active accretion can become extremely difficult to detect, even though its gravity remains substantial. A neutron star in a binary system may reveal itself if gas flows from its companion. Falling matter heats to very high temperatures and can produce X-rays. The visible star in this system does not necessarily fill the region in which its gas would be drawn away, so strong accretion may be absent. Without a stream of matter, an old neutron star could remain quiet. The lack of X-rays therefore constrains active accretion but does not exclude a dormant neutron star. If the collapsing stellar core is too massive for neutron pressure to support, collapse continues and a black hole forms. A black hole is a region where gravity becomes so strong that an event horizon surrounds the collapsed mass. The event horizon is the boundary beyond which light cannot escape. A stellar mass black hole may contain several times the mass of the Sun while occupying a region far smaller than any ordinary star. A black hole does not emit visible light from a surface. It becomes detectable mainly through its effects on nearby matter and objects. Gas falling toward it can form a hot accretion flow and produce X-rays. A companion star can orbit an unseen mass, revealing the black hole through motion. Gravitational lensing can bend light from background sources. If none of these effects produces a strong signal, an isolated or weakly fed black hole can remain electromagnetically dark. Each remnant class, therefore, leaves a different combination of mass, radius, temperature radiation, and gravitational influence. A white dwarf may be faint, but still emits cooling light from a surface roughly the size of Earth. A neutron star has a much smaller surface, may emit pulses or X-rays, and usually occupies a higher masses range. A black hole has no visible surface and can remain dark unless surrounding matter releases energy. The age of Omega Centauri allows all three classes to exist. Many generations of stars have already completed their evolution. White dwarfs should be common because low-mass stars are numerous. Neutron stars and black holes are rarer because they descend from massive stars, and some are expelled from clusters by asymmetric supernova kicks or later gravitational encounters. Others may remain bound, especially in a massive system with deep gravity. The hidden companion must be compared with these possibilities without assuming its identity. Its inferred mass, lack of light, orbital behavior, and absence of strong, high-energy emission define the tests. No single property decides the answer, because every interpretation must satisfy the complete pattern of evidence. Stellar evolution provides the available remnant types, while the observations decide which portions of that remnant family remain physically consistent with the system. A white dwarf offers the least exotic compact explanation for the hidden companion. It is a common product of stellar evolution, and Omega Centauri contains many old stars that should already have produced large numbers of these remnants. A white dwarf can preserve a substantial amount of mass while emitting far less light than a main sequence star. The central question is whether one can be massive enough to explain the orbit and faint enough to remain below the observational limit. The mass of a white dwarf is not determined only by its present temperature. It reflects the original star, the amount of material lost during giant phases, and the composition of the remaining core. Most white dwarfs have masses near a little more than half the mass of the Sun. Some are lighter, often because binary interaction removes the outer layers before normal evolution is complete. Others are heavier, approaching the upper limit allowed by electron degeneracy pressure. The orbital solution must overlap this physically permitted range. A typical white dwarf begins with a carbon and oxygen interior surrounded by thin layers of helium and hydrogen. The interior no longer supports ordinary fusion. Instead, densely packed electrons resist further compression. This pressure depends on quantum mechanics rather than temperature, so the star remains supported even as it cools. The cooling surface continues to radiate stored heat, and the luminosity declines gradually over time. Age strongly affects detectability. A young white dwarf can be hot blue and easy to see despite its small size. An old white dwarf becomes cooler and redder, and its total light falls. Omega Centauri is ancient, so a remnant formed early may have cooled for many billions of years. Such an object could be much fainter than the visible star. Cooling models estimate how bright it should remain at a given mass composition and age. These models include several physical processes. Heat escapes from the dense interior through the outer envelope. The core slowly crystallizes as ions settle into an ordered structure, releasing additional energy and delaying cooling. The atmosphere controls which wavelengths carry the escaping radiation. Hydrogen-rich and helium-rich atmospheres can produce different colors at the same temperature. Collisions between particles also alter opacity. In very cool atmospheres, each effect influences the expected brightness in Hubble's filters. Astronomers compare the detection limits with these cooling tracks. If a white dwarf of the required mass and maximum plausible age should still appear brighter than the observed limit, that solution becomes unlikely. If the predicted light falls below the threshold, the object may remain viable. The comparison must use the cluster distance and dust absorption because both affect the apparent brightness. It must also account for the visible star's light, which can hide a faint neighbor at small separation. A massive white dwarf is generally smaller than a lighter one. Stronger gravity compresses the electron-supported matter, reducing the radius. The smaller surface can lower the luminosity at the same temperature, but massive white dwarfs also have different cooling histories. Their interiors contain more stored energy, yet crystallization and neutrino emission can change the rate at which that energy disappears. The relation between mass, age, and brightness is therefore not a simple straight decline. The upper mass limit provides the strongest restriction. An ordinary non-rotating white dwarf cannot remain stable above roughly 1 4/10 times the mass of the Sun. Near this boundary, called the Chandrasekhar limit, electrons become highly relativistic, and their pressure can no longer balance gravity if more mass is added. Rotation or unusual composition may shift the exact threshold slightly, but not enough to allow an arbitrarily heavy white dwarf. If the orbital probability distribution lies mostly above this boundary, a single white dwarf cannot explain the companion. If only the lower edge overlaps the allowed white dwarf range, then the interpretation requires an orbital orientation distance or visible star mass near one end of its uncertainty. Such a solution is not impossible, but it is less strongly supported than one that fits the central values naturally. Spectral evidence adds another test. A hot white dwarf may contribute ultraviolet or blue light, even when it is faint in red filters. Its broad hydrogen or helium absorption features could alter the combined spectrum. Deep ultraviolet observations are especially sensitive to a warm remnant beside a cooler star. The absence of excess short-wavelength light limits the temperature and therefore the cooling age of any hidden white dwarf. A cool white dwarf is harder to find, but it still possesses a surface. It may emit weak optical and infrared radiation, and its atmosphere may create colors unlike those of ordinary low-mass stars. Photometric measurements across several filters search for this additional component. The target's light remains consistent with one visible stellar atmosphere within the measurement errors, leaving little room for a white dwarf brighter than the established limits. Binary history must also remain physically plausible. A white dwarf companion begins as a normal star that evolves, expands, and loses its outer envelope. If the current orbit is compact, the expanding giant may once have interacted with the visible star. Gas transfer or a shared envelope can shrink and reshape the orbit. These processes may leave the visible star with unusual mass rotation or chemical composition. The lack of strong anomalies does not exclude past interaction, but it constrains how disruptive that history could have been. A very wide earlier orbit could avoid direct interaction, yet mass loss changes the system. When the progenitor sheds material, the orbit generally expands because the total bound mass decreases. The present period and separation therefore carry information about the earlier configuration. Evolutionary models test whether a plausible progenitor can produce the current system without unbinding it or leaving an orbit inconsistent with the measurements. The white dwarf explanation remains a balance between familiarity and constraint. White dwarfs are expected in Omega Centauri, can be old and faint, and naturally provide hidden mass. Their permitted masses, cooling light, ultraviolet emission, and evolutionary history are limited, however. The observations allow only those models that fit all of these conditions at once. As the orbital mass estimate and photometric limits become more precise, the remaining white dwarf region contracts toward a narrow boundary rather than a broad and comfortable solution. Its survival depends on every uncertainty, leaning in compatible directions. A neutron star provides a denser and more compact explanation for the unseen companion. It forms when the core of a massive star collapses after nuclear fusion can no longer support it. The collapse compresses matter to extraordinary density, leaving an object with more mass than the Sun packed into a sphere only a few tens of kilometers across. Such an object can exert the required gravity while contributing almost no visible light. The allowed mass range is the first comparison. Most measured neutron stars have masses near 1 4/10 times the mass of the Sun, though some are lighter and others approach or exceed twice the Sun's mass. The precise upper limit remains uncertain because it depends on the behavior of matter at densities beyond those found in atomic nuclei. If the orbital solution falls within this range, a neutron star remains physically possible. If it lies well above it, the explanation becomes difficult. The visible star's orbit does not reveal the companion's radius, only its mass. This makes a neutron star easy to hide in images. Its surface area is tiny compared with that of a normal star or white dwarf. Even when the surface is hot, the total visible brightness can be weak because so little area is radiating. An old neutron star can cool for billions of years until its thermal glow becomes extremely faint. Cooling begins rapidly after formation. A young neutron star loses energy through neutrinos, then more slowly through radiation from its surface. The cooling rate depends on its mass, internal composition, magnetic field, and whether unusual particles or phases exist deep inside. The exact details remain uncertain, but old neutron stars are expected to be much dimmer than young ones. In an ancient cluster, a remnant formed early may no longer be detectable in visible light. Some neutron stars remain bright because they rotate rapidly and possess strong magnetic fields. Charged particles moving through those fields can produce beams of radio waves, visible light X-rays, or gamma rays. When a beam sweeps across Earth, the object appears as a pulsar. The absence of detected pulses does not exclude a neutron star. The beam may point elsewhere, the pulsar may have slowed, or the radio signal may be too weak to separate from the crowded background. X-ray observations provide another test. A hot young neutron star can emit thermal X-rays from its surface. An older one can produce X-rays if gas falls onto it. In a binary material from the visible star may be captured if the orbit is tight enough or if the visible star loses gas through a wind. Falling matter gains energy as it approaches the compact surface, heating to millions of degrees and releasing radiation. No bright X-ray source at the system's position would argue against active accretion. The absence of strong X-rays still permits a dormant neutron star. The visible star may lose very little gas, and the orbital separation may be too wide for efficient capture. Even captured material can remain weak if the flow is thin or disrupted by magnetic fields. Astronomers, therefore, use the X-ray limit to constrain the rate of accretion rather than to prove that no neutron star exists. A neutron star may also reveal itself through its influence on the visible star's spectrum. If the orbit is inclined towards the line of sight, the visible star should show repeating radial velocity changes. These changes arise from orbital motion, not from the neutron star's radiation. Combining radial velocity with Hubble astrometry can determine the full orbit more securely and refine the companion mass. A result centered in the neutron star range would strengthen this interpretation. The system's history must also be considered. A neutron star forms in a supernova or through another collapse process. A supernova can eject much of the progenitor's mass suddenly. It can also give the remnant a kick if the explosion is asymmetric. Either effect may disrupt a binary. For the present pair to survive the mass loss, and kick must leave the system bound. Some binaries do survive, but the allowed conditions depend on the original orbit and stellar masses. Omega Centauri's strong gravity can retain some neutron stars, though many may escape. A kick directed outward can carry the remnant beyond the cluster. A smaller kick, or one oriented favorably, may leave it bound. Over time, repeated gravitational encounters can move neutron stars toward denser regions because they are heavier than many ordinary stars. They can exchange companions, enter new binaries, or be ejected through later encounters. The current visible star may therefore not be the neutron star's original partner. In a dense cluster, a neutron star can pass close to a binary and replace one of its members. This exchange interaction tends to place the heavier object into the bound system. The resulting orbit may differ from the orbit produced by ordinary isolated binary evolution. Such interactions are uncommon for any one star, but become important across billions of years in a massive cluster. A neutron star companion could also affect the visible star through past mass transfer. If the neutron star once accreted gas, it may have spun faster and become a recycle pulsar. The donor star could lose mass and show altered chemistry. The visible star appears broadly ordinary, so any such interaction must either have been mild, ancient, or hidden within measurement uncertainty. Cluster exchange provides a route that avoids requiring direct evolutionary contact between the current pair. The evidence therefore supports a conditional possibility. A neutron star naturally combines substantial mass with very little optical light. Its lack of a visible surface large enough to brighten the system fits the photometric limits. The absence of detected pulses or X-rays does not remove it because old dormant neutron stars can be quiet and their beams can miss Earth. Its main challenges arise from the orbital mass, the system's survival after formation, and the lack of a compact object signal. Further observations can test this interpretation. Deeper radio searches may detect weak pulses or place stronger limits. Sensitive X-ray measurements can search for a cooling surface or faint accretion. Improved spectroscopy can refine the orbital inclination and mass. Until those measurements narrow the range, the neutron star case remains physically credible, observationally quiet, and not uniquely established. A black hole offers the most compact explanation for a companion that carries substantial mass while producing no detectable surface light. It forms when gravity overwhelms every known form of pressure supporting a collapsed stellar core. The resulting object is defined by an event horizon, a boundary from which light cannot escape. Outside it, gravity behaves like that of any object with the same mass. The orbital motion of the visible star is therefore the main signal. A black hole does not need to shine in order to reveal itself. Its mass bends the path of the companion, changes the star's velocity, and fixes the timing of the orbit. If the infrared mass lies above the stable range, for white dwarfs and neutron stars, a stellar mass black hole becomes the natural compact possibility. The conclusion depends on the full probability distribution rather than one value. Stellar mass black holes usually form from massive stars. After the central fuel is exhausted, the core collapses. In some cases, an explosion expels the outer layers and leaves a black hole. In others, much of the star may fall inward with only a weak, outward explosion. The final mass depends on the original star wind's composition, rotation, binary interaction, and collapse. Omega Centauri is old enough for many massive stars to have completed this evolution long ago. Those stars live briefly compared with low-mass cluster members. They burn fuel, rapidly evolve through successive fusion stages, and die within millions of years. Any black holes they create can remain for billions of years if they are not ejected. Their presence is therefore compatible with the age of the cluster, even though their progenitor stars are gone. Retention remains uncertain because black holes can receive kicks during formation. Uneven mass ejection, asymmetric neutrino emission, or motion within a binary may give the new remnant additional velocity. A strong kick can carry it out of the cluster. A weaker kick may leave it bound. Omega Centauri's large mass and deep gravitational potential improve the chance that some black holes remain compared with smaller clusters. After formation, black holes interact gravitationally with surrounding stars. Because they are heavier than most cluster members, repeated encounters tend to move them toward denser regions. This process transfers energy between objects and gradually sorts the population by mass. Black holes can form temporary pairs, exchange companions, harden existing binaries, and eject one another through close interactions. Over billions of years, the cluster may lose many black holes while retaining some isolated objects and binaries. The visible star may become bound to a black hole through ordinary binary evolution or through a later exchange encounter. In the first case, both objects begin as stars in the same system. The massive star evolves first, loses material, and collapses. The binary survives only if the mass loss and any kick do not unbind it. In the second case, a black hole encounters an existing binary and replaces one member, producing a partnership unrelated to the original stellar evolution. A black hole in a binary is often discovered through accretion. If gas flows from the visible star toward the black hole, the gas forms a rotating structure and heats through friction and compression. This material can emit strong X-rays before crossing the event horizon. The black hole itself remains dark, but the surrounding flow becomes bright. The absence of a luminous X-ray source therefore indicates that little material is currently falling inward or that the flow radiates inefficiently. The visible star may not fill its Roche lobe, the region around it where matter remains gravitationally attached. If the star stays well inside this boundary, direct mass transfer does not occur. A weak stellar wind can still send some gas toward the black hole, but an old low-mass star may lose material slowly. At a moderate orbital separation, only a small fraction of that gas is captured. The expected X-ray emission can then fall below current detection limit. Low accretion rates also change the structure of the flow. Instead of forming a bright, thin disk, the gas may remain hot, diffuse and inefficient at converting gravitational energy into radiation. Much of the material can be expelled again before reaching the horizon. A quiet black hole can therefore exist in a binary without resembling the luminous systems first used to establish stellar black holes. Radio observations may search for weak emission from particles near the black hole. X-ray and radio limits can be combined with models of gas capture, but these models depend on the uncertain wind from the visible star and the local environment. A non-detection constrains active feeding more strongly than it constrains the black hole itself. Gravity remains the cleaner measurement because it depends directly on the orbit. Gravitational lensing provides another possible effect. A compact mass bends light passing nearby. If the black hole moves in front of a background star, the background source may brighten or shift position temporarily. In a dense cluster, alignments can occur, though predicting one for a particular object is difficult. The visible companion itself does not usually pass behind the black hole from Earth's viewpoint, unless the orbit is aligned closely enough. The orbit may also show relativistic effects, but they are expected to be very small for a wide stellar binary. The closest separation, total mass, and measurement precision determine whether the orientation of the ellipse changes detectably over time. In most cases, Newtonian gravity describes the observed motion well. Relativity becomes essential near the event horizon, far inside the scale traced by the visible star. A black hole interpretation must still survive alternative explanations. A neutron star can remain dark and occupy part of the same mass range. A massive white dwarf may fit the lowest allowed solutions. Several faint objects can imitate one mass under limited conditions. Improved orbital coverage is needed to determine whether the companion lies clearly beyond these possibilities. The strongest black hole case emerges when the central mass estimate exceeds the maximum stable neutron star mass. The astrometric orbit remains secure, and no luminous companion appears at the required location. Until those conditions are satisfied with narrow uncertainty, the object remains a candidate rather than a confirmed black hole. Its defining evidence is a persistent gravitational pull from a region where ordinary starlight is absent. The hidden companion is constrained by a chain of measurements, and each link carries uncertainty. The orbit appears ordered, the extra mass appears necessary, and the missing light appears significant. Yet none of these conclusions rests on an exact value. Astronomers therefore examine how every assumption influences the result. The goal is not to weaken the evidence, but to understand which parts remain firm and which parts may shift as new observations refine the system. The first uncertainty lies in position. Hubble measures the center of a stellar light pattern on a detector, not the star itself as a resolved sphere. Crowding focus detector response and the wings of nearby stars can move the measured center by a tiny amount. These effects are corrected with calibration models, but the correction is never flawless. Repeated exposures help because random errors scatter in different directions, while a true orbital signal remains coordinated. The reference frame introduces another source of uncertainty. The target's motion is measured relative to surrounding stars that also move through Omega Centauri. Their velocities are small but not zero. A large reference sample reduces the effect of any one star, yet the selection of reference stars can alter the transformation slightly. Astronomers repeat the analysis with different groups excluding stars affected by saturation, blending, or unusual motion. A robust result should remain similar across these choices. Geometric distortion also matters. The camera does not map the sky onto the detector with perfect uniformity. The distortion changes with detector position and can vary with temperature, focus, and time. Calibration maps correct most of this pattern. Observations taken at different telescope orientations provide a useful test, because the same sky motion then falls across different parts of the detector. If the infrared orbit survives these changes, confidence increases that it is not produced by one local instrumental defect. The distance to Omega Centauri affects the physical scale of the orbit. Hubble measures angular displacement, and the conversion to a separation depends on how far away the cluster lies. A larger distance means a larger physical orbit for the same angle, which changes the infrared mass. Distance estimates come from several methods, including variable stars, stellar population modeling, and geometric measurements. They agree within a range, but the remaining spread must be carried into the orbital solution. The visible star's mass is also model-dependent. Its brightness and color are compared with theories of stellar evolution. Yet those theories require assumptions about age, chemical composition, helium abundance, and internal mixing. Omega Centauri contains several stellar populations, so assigning the star to one group is important. A small change in the visible star's mass changes the amount of mass attributed to the hidden companion. The effect may be modest, but it becomes important near the boundaries between white dwarfs, neutron stars, and black holes. Orbital inclination creates an ambiguity. Hubble records motion across the plane of the sky, but part of the true motion may point toward or away from Earth. A tilted orbit can appear smaller than it really is. Spectroscopy helps by measuring radial velocity, yet the star may be faint and crowded light can reduce precision. If radial coverage is incomplete, several inclinations can fit the data. Each inclination produces a different combination of speed, separation, and companion mass. The period and eccentricity can also remain connected. When observations cover only part of a cycle, a long orbit seen near rapid motion may resemble a shorter orbit with a different shape. Measurements near closest approach strongly influence the fitted mass, because acceleration changes most rapidly there. Missing that interval allows a wider family of solutions. Even when a complete cycle is suggested, sparse sampling can leave uncertainty in where the fastest and slowest phases occur. The assumption of two bodies is another testable simplification. A single companion produces a clean Keplerian ellipse, but a compact multiple system can create a similar broad motion while adding smaller deviations. If those deviations lie below current precision, the data may still fit a two-body model. Astronomers inspect the residuals for repeated structure that could reveal an additional object. A lack of visible residuals limits such complexity, but does not prove that the companion is singular. The cluster environment contributes a weak background pull. Over the small scale of the orbit, this force acts almost equally on both bodies, so it should not dominate their relative motion. However, nearby passing stars can create slight perturbations. The probability depends on local stellar density, encounter speed, and orbital size. Dynamical models estimate whether such perturbations matter during the observing span. In most accepted solutions, they remain smaller than the measured orbital signal, though they still belong in the uncertainty budget. The absence of light has its own limits. Detection thresholds depend on wavelength, crowding, exposure, depth, and the assumed position of the companion. A faint source may hide within the visible star's light pattern or behind an unrelated neighbor. Artificial star tests measure how often such sources would be recovered, but recovery is expressed as a probability rather than certainty. The conclusion is therefore that a companion brighter than a certain range is unlikely, not that the region contains no photons from another object. High-energy non-detections must be treated with similar care. A quiet neutron star or black hole may emit less X-ray or radio radiation than current instruments can detect. The predicted emission depends on uncertain gas capture, magnetic fields, rotation, and viewing direction. A missing signal constrains active states more strongly than dormant ones. It cannot identify the companion alone. When all uncertainties are combined, the result is a family of allowed models. Some require ordinary but narrowly tuned conditions. Others favor a compact remnant with little or no detectable light. The central solution may suggest one class while the edges still overlap another. Scientific caution preserves this structure rather than replacing it with a single dramatic label. The mystery still remains because the measurements are strong enough to reveal an unseen gravitational presence, but not yet narrow enough to determine its nature without ambiguity. The star's motion is real within the tested reductions, and the missing light is meaningful within the established limits. What remains uncertain is the exact mass, the full three-dimensional orbit, and the identity of the object occupying the dark center. The final stage of the investigation depends on extending the record. The visible star has already traced part of a controlled path around an unseen center, but every new measurement can reduce the range of possible orbits. Continued astrometry remains the most direct requirement. Hubble and other observatories capable of comparable precision can return to the field and measure the star at additional points along its motion. A longer baseline separates a true repeating orbit from slow curvature produced by an incomplete fit. The most valuable observations occur where the star changes speed and direction most rapidly. Near the closest part of an eccentric orbit, gravity produces the strongest acceleration. Measurements made there constrain the total mass and orbital shape more tightly than measurements made during slower motion. Accurate scheduling, therefore, depends on the current orbital model, even though that model still carries uncertainty. Several visits spread across the expected rapid phase reduce the risk that one exposure or one calibration choice dominates the result. Astrometric observations at different telescope orientations also remain important. When the detector is rotated relative to the sky, the same stellar displacement falls across different picture elements and optical regions. A real orbit remains fixed on the sky while some instrumental effects change. With detector placement, repeated measurements through multiple filters provide another independent test. The orbital signal should appear consistently even when the companion contributes different amounts of light at different wavelengths. Spectroscopy supplies the missing motion along the line of sight. Repeated spectra can track the visible star as it approaches and recedes during the orbit. The timing and amplitude of these radial velocity changes determine the orbital inclination and help convert the apparent sky path into a three-dimensional orbit. Inclination is one of the main reasons several companion masses can fit the same astrometric curve. Better radial coverage can therefore move the inferred mass away from one remnant class and into another. High spectral resolution is needed because the expected shifts may be small and the star lies in a crowded field. Light from nearby cluster members can enter the observing aperture and contaminate absorption lines. Instruments with stable wavelength calibration, narrow spatial sampling, and repeated observations can reduce this problem. The measurements must also account for convection surface activity and instrumental drift. A periodic velocity pattern matching the astrometric phase would strongly support the orbital interpretation. Spectra can search for hidden light at the same time. A faint white dwarf may contribute broad hydrogen or helium features, especially at shorter wavelengths. A low-mass star may add cool molecular bands or a second set of narrow absorption lines. If no secondary spectrum appears, the upper limit on companion brightness becomes stronger. Ultraviolet observations are particularly useful for detecting a warm white dwarf whose visible light is overwhelmed by the ordinary star. Infrared measurements test the opposite temperature range. Very cool stars and brown dwarfs emit a larger fraction of their radiation at long wavelengths. Deep infrared imaging may reveal excess light that optical filters miss. The crowded cluster still creates confusion, so sharp resolution remains essential. A consistent infrared source moving with the predicted orbit would support a faint ordinary companion, while a strict non-detection would further reduce that possibility. X-ray observations can examine compact remnants. A neutron star may emit weak thermal radiation from its surface or brighter emission from captured gas. A black hole may produce X-rays if even a small accretion flow forms around it. Deeper exposures can search for faint emission at the astrometric position. A detection with the correct location and variability could distinguish an active compact object, though its spectrum and luminosity would still require interpretation. Radio observations provide a separate route. A neutron star may emit pulses even when it is faint in X-rays, but the beam must cross Earth. Long observations across several radio frequencies can search for weak periodic signals and correct for dispersion by material between the cluster and Earth. A non-detection cannot remove the neutron star possibility, yet it constrains the population of active pulsars and the range of beam and luminosity models. A black hole may produce weak radio emission from a low-rate accretion flow or a small outflow of particles. Combining radio and X-ray limits can test whether gas is being captured efficiently. These comparisons depend on the uncertain wind from the visible star and the density of surrounding gas. The cleanest black hole evidence therefore continues to come from mass rather than from the absence of radiation. The cluster environment can also be studied more precisely. Better maps of stellar density and internal motion near the target help quantify the probability of passing perturbations, exchange encounters, and compact multiple systems. Long-term monitoring of nearby stars can reveal whether the local reference frame contains unnoticed binaries. Improved distance measurements to Omega Centauri reduce the conversion uncertainty between angular orbit and physical separation. The visible star itself requires continued characterization. More precise temperature, chemical abundance, rotation, and surface gravity measurements refine its mass. A smaller uncertainty in the visible star's mass leads directly to a smaller uncertainty in the hidden companion's mass. Chemical evidence may also reveal whether past mass transfer occurred, which would favor some evolutionary histories over others. No single future observation is guaranteed to identify the object. The strongest conclusion will emerge when independent methods converge. Astrometry must define the orbit, spectroscopy must establish the three-dimensional velocity. Photometry must limit hidden light, and high-energy searches must test compact activity. Agreement among these measurements can place the companion securely below, within, or above the stable mass ranges of white dwarfs and neutron stars. Until that convergence occurs, the invisible object remains defined by gravity. The visible star continues to mark its presence through a slow and measurable orbit. Each new position narrows the possible mass. Each spectrum clarifies the direction of motion, and each deeper image tests whether ordinary light is present. The mystery persists at the boundary between what the measurements already require and what they have not yet distinguished. The process remains gradual because orbital certainty grows through time rather than through one deep exposure. The star must move, instruments must return, and independent teams must reproduce the result. This slow accumulation protects the conclusion from error and allows the unseen companion to be classified by evidence alone. Across the quiet field of Omega Centauri, the visible star continues along its measured path. Its light remains steady enough to be followed while the center of its orbit remains dark. Nothing in the image announces the nature of the companion. The evidence rests in small changes of position gathered across years and compared with the motion of surrounding stars. The cluster itself moves through the halo of the Milky Way, carrying millions of old stars through a region shaped by gravity and time. Within that larger movement, one ordinary point of light traces a smaller curve. The curve records the pull of mass that does not reveal itself through ordinary brightness. It may belong to a faint remnant, a quiet neutron star, a black hole, or another configuration still allowed by the measurements. The present observations narrow the possibilities without forcing a final name. Science remains at this boundary with patience. Each new image adds another position. Each spectrum adds another part of the velocity. Deeper searches test for weak light radio pulses or X-ray emission. The result grows slowly from agreement between separate methods rather than from one dramatic signal. For now, the visible star continues its orbit in silence. Its motion preserves the shape of an unseen gravitational presence while the crowded cluster shines around it. The mystery remains real, but it also remains measured. It belongs to the careful space between detection and identification where uncertainty is not emptiness but a precise description of what the evidence has not yet resolved. The distant light continues across space, carrying the quiet record of the system toward Earth.